Hey everyone. So this quick video will be all about how a neuron communicates. Okay, so in general, communication can be broken down into electrical communication and chemical communication, or electrical transmission and chemical transmission. But we're going to start with electrical transmission. So let's begin with a neuron at rest. It's not doing really anything. Okay? Well, the inside of that neuron is made to remain relatively negative compared to the outside of the neuron. So the charge, or the resting potential of the membrane, is on average negative 70 millivolts, meaning that the inside is around negative 70 millivolts, more negative than the outside. Now, how does that neuron stay that way? Well, one of the ways it stays that way is by use of what are called sodium-potassium pumps. Now, sodium and potassium are both positively charged ions. Okay? So, in order to keep the inside relatively negative, positive sodium ions need to stay outside. And you would think so to potassium, but the neuron wants to stay at around negative 70 millivolts. And if it didn't have any positive ions in there, it would just run off into negative infinity. So it needs to keep a little bit of positive potassium ions inside to keep it from going off into negative infinity. But it pumps out twice as much sodium as it pumps in. So it's twice as much sodium as it's pumping potassium in. So you have twice as much sodium leaving the neuron as you have potassium entering. Okay? So, in addition, you also have a bunch of negatively ionized proteins, or amino acids, inside the nucleus of the cell. So, the inside of the cell, the neuron, is negatively charged compared to the outside. So the resting potential, or the resting charge of the neuron, is negative 70 millivolts. Now, how do we get that neuron to become active, to send a signal? Well, in order to do that, you have to change the charge of the membrane. Now, how can you change? The charge of the membrane can be changed in two ways. First, before I talk about how it can be changed, I need to talk about the term polarized. So, the antithesis of polarization is neutral. So, neutral is represented by 0. And the further away in any direction that you get from 0, the more polarized you are. So negative 100 is equally polarized as positive 100. Okay? So, anytime I move further away from 0, I'm hyperpolarizing. So if I move from 100 to 200, or from negative 100 to negative 200, then I'm hyperpolarizing. But anytime I'm moving towards 0, okay, yes, I'm a 0. Anytime you're moving towards 0, you're depolarizing. Okay? So if I move from 100 to 50, or to 30, or to 10, or even to 0, I'm depolarizing. If I move from negative 100 to negative 50, or negative 30, or negative 10, or even to 0, I'm depolarizing. Okay? So, this is a plot of the charge of a neuron. Now, in order for a neuron to become active, that neuron has to hit what's called the threshold of excitation, and it's indicated here. So the average threshold of excitation is negative 65. Now, what you notice is that negative 65 is less than negative 70. So the average threshold of excitation is less than the average resting potential. In order for that cell to become active, the resting potential has to equal the threshold of excitation. So, in order for a neuron to become active by hitting its threshold of excitation, it has to move closer to 0, or depolarize. If something happens to the neuron to make it more negative, so to move from negative 70 to negative 80 or negative 90, then it's been hyperpolarized. Okay? Now, because depolarization causes the cell to move closer to the threshold of excitation, then it increases, because moving closer to the threshold of excitation increases the chances of an action potential, then all things that depolarize the neuron have an excitatory effect because they increase the chances of the neuron becoming excited. Anything that hyperpolarizes the neuron, anything that moves it further away from zero and further away from the threshold of excitation, lowers the chances of that neuron becoming excited. So it inhibits the ability of that neuron to become active, to wake up. So anything that hyperpolarizes the neuron has an inhibitory effect. Anything that depolarizes the neuron has an excitatory effect. Now, a neuron can get multiple inputs from multiple sources all at the same time. And what happens is that the neuron basically adds them all up. Okay, so for example, here we have some diagrams of the input that a neuron might get from 4 different sources. Okay, so here we have 2 sources giving. So here and here, we both have situations where 2 sources are giving positive or excitatory effects. They're trying to depolarize the neuron, and 2 inhibitory effects, or 2 other sources are trying to hyperpolarize the neuron. So what happens if these are equal effects? Then the negatives cancel out the positives. So this has a net result of no change in resting potential. This has the effect of no change in resting potential. The bottom 2 is a different situation altogether. Here we have only inhibitory signals. So we have 4 different inputs hyperpolarizing that neuron. It's going to make that neuron, it's going to be very unlikely for that neuron to charge. It is being inhibited by a large extent. Here, however, all we have from all 4 inputs are excitatory signals. So we have a high likelihood, it's very likely that that neuron is going to equal its resting potential, reach its threshold of excitation and achieve an action potential. Now, if that neuron does not reach the threshold of excitation, then it will not become excited, no matter what. If it doesn't hit the threshold, it won't fire. End of story. And in fact, if no more inputs come in, it'll eventually go back to its resting potential. However, if enough excitatory effects come in that it hits the threshold of excitation, then an action potential will be achieved. You will see a spike in the charge of that neuron. So this spike is your action potential. And it's going to increase to the charge of the membrane is going to reach its peak charge every time. So if the neuron fires, it's going to hit its peak. So if it hits the threshold of excitation and an action potential occurs, that action potential will hit its peak every time. It will never be weaker, it'll never be stronger. If the action potential occurs, it occurs to its maximum strength. If it doesn't occur, if an action potential doesn't occur, if the threshold of excitation is not reached, then the action potential will not occur at all. Not even a little bit. If the threshold of excitation is not reached, nothing even remotely resembling an action potential will occur. Okay? That all or none is referred to the all or none principle. If the threshold is reached and the action potential occurs, that action potential will occur to its full strength. All. If that threshold is not reached, then that action potential will not occur at all. It won't even start. No. So, an action potential is all or none. Okay? Now, as you can see, it's a huge change in voltage. I mean, sometimes it can be around 150 volt change. So here it's changed from a resting potential of negative 70 millivolts to positive 30. So it's a huge change. Now, after the action potential hits its peak, all those sodium channels shut. So when the threshold is hit, all the sodium channels open. Sodium floods in. We hit its peak, the action potential is achieved, all the sodium channels close, and all the sodium-potassium pumps start pumping out sodium like crazy. And at this point, they don't let any potassium back in. This brings the charge of the neuron way back down, even dropping below its original resting potential. But then the potassium pumps start working again, and they start slowly pumping potassium back in, and it slowly rises back to its resting potential. Now, that is all happening in the cell body. Well, then what happens is that action potential will start traveling down the axon. I'm going to grab that picture that I showed in the earlier video. So everything we've been talking about has been happening right here in the cell body. Well, now the action potential goes down the axon. And it does it like a wave, like at a stadium. So some people at one part of the stadium start doing that. Well, then then the wave travels all around the stadium, unless it hits the rival fans, they don't like it. So that's exactly how an electrical charge travels down the axon. So imagine that people in the stadium are the little sodium-potassium pumps on the axon, and imagine the whole ring of the stadium is the axon itself. When people stand up, you can imagine like that's the sodium pumps opening, and sodium rushing in, and the charge jumping. Okay, so as the wave goes around, sodium pumps are opening, sodium rushing in, and the charge goes up, just like the people. Okay, and then the charge travels down the axon, just like the wave, and it goes all the way around, just like going from the beginning of the axon all the way to the end. Now, you remember those myelinated sheaths, those segments of glial cells that can coat the axon? Well, I told you that those have the ability of conducting the charge. What that means is they can make the charge travel down the axon faster. They can make the wave go through the stadium faster. Well, how? Well, let's imagine that in the stadium you have these tarps, okay? And when the wave hits the tarp, the wave just picks up immediately on the other side of the tarp. So the wave didn't have to travel through the tarp, okay? It just jumped, basically. It just started at the end of the tarp. Well, that's what a myelinated segment does. So the charge goes to the beginning of the myelinated segment and then jumps to the next node of Ranvier. Remember those bare patches of axon? It then travels down that next node of Ranvier, just like it would, like the wave would in the stadium, until the next tarp is reached. And then the wave starts at the end of that tarp, and it continues on. That's exactly how the axon travels down a myelinated axon. If there were no if you have an axon without any myelin, any glial cells wrapped around it, then it would be like the wave going through a stadium without any tarps. It would have to go the entire distance, and it wouldn't be able to jump. Okay, so that's the function of those myelinations, of those glial cells myelinating the axon. Now, you remember at the end of the axon you had those axon terminals, like that. See? You remember the synaptic vesicles inside the axon terminal? Well, when that charge gets to the axon terminal, what happens is those synaptic vesicles move towards the membrane, and they open up into a gap between the current neuron and the next neuron. That gap is called a synapse. Now, the neurotransmitters that are in those synaptic vesicles get released into that space, into that synapse. Those neurotransmitters all change the charge of the next neuron. Now, when a neuron gets used, it gets broken down. But some of the neurotransmitters, so when a neurotransmitter is used, it gets broken down. But when it's not used, one of two things happen to it. First, it gets reuptaken into the neuron that had originally released it. That process is called reuptake. The other thing that can happen is enzymes come into the gap, the synapse, and actually break the neurotransmitter down. Okay? You can call that decay. So those are the two things that happen. Now that last piece from the the synaptic vesicles releasing the neurotransmitter into the synapse. That's actually referred to as chemical transmission because the charge is now being carried across the gap with chemical. So it's chemically transmitting the charge. Whereas within the neuron, from the cell body all the way to the axon terminal, we're actually talking about electrical charge going down the length of the cell's membrane. That's electrical transmission. And there you have it. That's how a neuron takes a signal from somewhere else, sends it down the axon, and sends the signal to another. Boy, that's a great way to end it. And that's how it sends the signal to another neuron. All right, guys. Again, if you have any questions, send me an email, and I'll see you later.